Hello, welcome to Fundamentals of Acoustics. Today is the 5th day of the current week, and what we plan to discuss today is the notion of directivity. So, we know that if you have a spherical source, sound propagates equally in all the directions. So, that kind of a source is omnidirectional. But then if you have two sources which are interfering with each other, and suppose these two sources are very close to each other, and both these sources, even though they may not necessarily be out of phase, but if we are away from these two sources, the sound pressure level changes with respect to theta. So, the combination of these two simple poles or simple sources may not be necessarily spherical in nature, right. But then there could be a third situation where a specific source, for instance you have an engine block and it may be generating more sound in one particular direction and less sound in some other direction. So, sound sources have to be characterized not only in terms of the total amount of sound which they produce, but also in terms of how does sound pattern, how does sound pressure level change as I vary the angular orientation. So, this characterization of a sound source in terms of its directional characteristics is known as directivity. So, now there are several ways to quantify directivity. So, our goal for today is to talk about directivity. So, there are 3 or 4 ways in which directivity of a sound source can be quantified. So, the first one is directivity pattern. So, what is a directivity pattern? So, first we will define it and then we will actually show you what it is. So, it is a graphical representation graphical representation of a sound source or actually sound sources emissions as a function of direction in a specified plane and at a specified frequency. Okay. So, now we will explain what it means. So, let us consider some so let us consider a sound source and let us consider that it is small for starters. So, it may not necessarily be a point, but a non-zero size, and first let us define the directions. So, x, y and the plane through the board is the z plane. So, suppose I am interested in trying to understand that in the z plane, which means that the plane normal is the z axis. In the z plane, how is sound pattern changing? So, what I want to know is, so let us draw a z plane, a circle in a z plane. So, this is actually a bad circle because it does not place the source at the center. Okay. So, this is somewhat better. So, I want to, so our source is located at the center of this plane, and this is R, right. So, this is another position R, and this is theta, this is theta. So, what the directivity pattern tells us is that it gives us an idea that how does sound, or if I am measuring sound in sound pressure level in decibels, so how does SPL change as theta varies from 0 degrees to 360 degrees, from 0 degrees to 360 degrees when R is fixed. So, I cannot change R for a specific R. How does SPL change when theta varies from 0 degrees to 360 degrees? So, that is, and when R is fixed and so is the plane of observation and frequency of interest. So, that is what the directivity pattern gives. So, if we have a perfectly symmetric source, if it is a truly point source, then how will the directivity pattern look like? It will just look like a perfect circle. And what does this circle represents? The distance. So, this is my reference axis. This point tells us what is the value of pressure in decibels in dB as theta changes. So, for monopole, directivity pattern so directivity pattern is perfect circle. It is perfect circle, and it is in all planes and all frequencies. So, that is what we have for monopole, but you can have two sound sources, or you can have a source. So, but there could be another situation where but there could be other situations where you may have a directivity pattern something like this, or it could be something like this. What does this kind of a directivity pattern tell us? That sound is being transmitted more in at theta equals pi over 2 and negative pi over 2, but at 0 and pi radians transmission of sound is very less. You can have several lobes for such directivity patterns. So, source is always located at the center. So, all these are different directivity patterns, and here the distance from the center represents the amplitude in decibels, and the angular coordinate represents the angle at which you are measuring. But please understand that these directivity patterns are specific to frequency. There could be a sound source which produces almost circular directivity pattern for very low frequencies, but as you increase the frequency it may be very complicated directivity pattern. So, it is important to understand that directivity patterns can change with respect to frequencies and also with respect to the plane of observation. So, that is the first way to quantify directivity. The next parameter which is used is called directivity factor. So, this is the second measure for directivity. So, what does this mean? Suppose you have a sound source. Suppose we have a sound source. So, actually before talking about directivity factor, we will talk about beam width, because directivity factor is dependent on this understanding of beam width. So, the second parameter which we will discuss is called beam width. So, suppose we have a sound source and let us say this sound source is emitting sound in this direction at maximum possible level. So, this direction corresponds to, so this is our reference direction, and this corresponds to direction of maximum SPL. Okay. So, consider a loudspeaker, suppose. So, this is sound source, maybe in this direction the sound pressure level is maximum, but maybe it is not that much in this direction. So, that is our reference direction. Then now this, again going back to the example of loudspeaker, the sound is going in a particular direction. So, it is going in shape of a kind of a beam. Okay. So, we want to define how wide that beam is. Now, theoretically the beam will be in all the directions, sound will be emitted in all 360 degrees of all the 360 degrees, but we still want to define how strong this directionality is of the speaker or the sound source. So, what we do is we take some radius. So, what we do is we first thing is we fix a radius value for radius. So, let us say we fix this value. So, we will say that okay, the radius is going to be this. So, this is my R. And then I will take a microphone and scan the pressure level, sound pressure level along this arc which has a radius R and the center is S. So, sound pressure level is going to be maximum on in the reference direction, but maybe at this location, so suppose here it is some decibels, 100 decibels, but here it goes down by let us say minus 3 dB or minus 6 dB, and here also it goes down by minus 6 dB. Okay. Then what I do is I create a geometry. So, the location where the sound pressure level falls by minus 6 dB, falls by 6 decibels, that location is identified and this angle is measured, and this angle is known as beam width. It is known as beam width. Okay. So, what is beam width? Beam width, it corresponds to the angle over which the sound pressure level for a fixed radius can drop, or it drops by as much as 6 decibels. And in this case, we use a particular reference direction, and the reference direction is chosen such that it corresponds to the direction where we measure maximum sound pressure level. So, that is beam width. The third parameter for measuring directivity is called directivity factor. But before we talk about directivity factor, I will like to reiterate this beam width is also, it can change with frequency. Okay, it is important. All these parameters, directivity, pattern, beam width, directivity factor, all these things, they depend on frequency. So, directivity factor. So, what does beam width tell? It tells us how much sound is being directed in a particular direction. It gives you that idea. Now, the directivity factor helps us compare how much directional a particular sound source is compared to a perfectly symmetrically radiating sound source. So, suppose we have a sound source. So, suppose we have a sound source S, sound source S1, and we are interested in finding out its directivity factor. Okay. So, let us consider this point P. So, the first thing to find directivity factor is to find some angle theta. What is this theta? So, at some point P for a given radius r, theta corresponds to direction where P or SPL is maximum. Okay. So, in some cases theta could be 0. So, what do? You take a microphone and at a distance r you scan and you locate a angle theta where sound pressure level is maximum. So, that is one thing you record, and so that is, so the first thing is that you identify theta. Second thing is you find out intensity. So, what is it intensity? It is watts per square meter corresponding to such point P. So, to such point where SPL is maximum. Okay. So, let us say that this intensity is I1. Let us say that this intensity is I1. Then the third step what we do is that we replace S1 by an ideal monopole. So, what is an ideal monopole? Which emits sound with equal intensity in all directions. So, you replace sound this source S1 by an ideal monopole source which produces same acoustic power as S1. So, you cannot just replace it with any monopole. Suppose the overall acoustic power which was being emitted by S1 was n watts, you have to identify an acoustic source which is emitting n watts of power, but it has to be a monopole or it has to be spherically symmetric. And for such a symmetric monopole, you measure intensity at point P, because you have already identified that point P. So, you will measure this intensity at point P and let this be I2. Then directivity factor, and this is again specific to a frequency, because you do this experiment for different frequencies. So, directivity factor for this particular source at frequency f is equal to I1 over I2, I1 over I2, and this will be always greater or equal to 1. It can never go down, because I1 is the, because point P is the direction in which maximum sound pressure level is sensed. Okay. So, it will always be there. And then the third thing is directivity index. So, lot of times it is referred as DI, and DI, which is again a function of frequency, it is equal to 10 log of 10 QF. So, these are 4 different parameters for directivity of a sound source: directivity pattern, which is a graphical representation; beam width, which tells us how strong a beam is in particular direction; directivity factor, which is comes out as a number; and directivity index. So, with that we conclude our discussion for today, and tomorrow will be the last day for this week, and what we will discuss tomorrow will be complex power flow for spherically symmetric sound sources. So, with that, have a great day, and we will meet once again tomorrow. Bye.